This is problem number 5 from the 2011 Form B of the AP exam. This was actually on the AB and the BC exam. And the problem setup is that someone is riding their unicycle back and forth along a straight east-west track. They tell us that this person's position is modeled by the function b, and it's a twice differentiable function, and we have various values of b, and b is measured in meters from the west end of the track. So at t is equal to 0, the person was 100 meters from the west end of the track, t equals 10, 136 meters from the west end of the track, and so on. This person's velocity measured in meters per second was also measured at various values of t. And then what we're asked to do in part A is we're asked to estimate this person's acceleration at t equals 5 seconds. So basically we're looking for A of 5. And if you recognize that acceleration is the rate of change of velocity, or the derivative of velocity, we basically just want an estimate for v prime of 5. So if we know our velocity graph has the point 0, 2 on it, and the point 10, 2.3 on it, the average rate of change of velocity on the interval from 0 to 10 would just be the slope of the line segment connecting 0, 2 to 10, 2.3. So I can estimate an instantaneous rate of change, or the slope of a tangent line, by using the slope of a secant line. So this is just a regular old slope formula here, and I have the difference in velocity values divided by the corresponding difference in t values. And if I simplify that, I end up with 0.03 meters per second squared, because velocity is measured in meters per second, and then time in the denominator here is measured in seconds. So that gives you your familiar units of acceleration, meters per second squared. If you're more comfortable dealing with fractions at this point, you can change 0.3 to 3/10. So 3/10 divided by 10 is like 3/10 times 1/10, which will give you 3/100ths, which I have the decimal form of right here. In part B, we want to interpret what this is going to represent. Since we are integrating speed here, the absolute value of velocity is speed, since we're integrating speed and not really taking into account the direction of the motion, this result is going to give us how many meters this person has traveled from t equals 0 to t equals 60. If you think about the units involved, v of t is measured in meters per second, dt is measured in seconds, take the product. These seconds will cancel, your answer is just going to be measured in meters, and it's again going to represent the total distance traveled from t equals 0 to t equals 60. If the absolute values weren't there, then it would just represent the change in position from t equals 0 to t equals 60. What we want to do is we want to estimate the value of this integral using a left Riemann sum with subintervals indicated by where we have our data points. So I went ahead and I plotted my velocity function. So I plotted my point at 0, 2, my point at 0, 2.3, and so on. And if I wanted to estimate the value of this with left Riemann sum, I was going to draw in my rectangle. So here's my first subinterval. My left endpoint would be here. The height of the function at that left endpoint is going to generate the height of this first rectangle. Here's my next subinterval, so a little wider subinterval. Here's the left endpoint of it. The height of my function at that left endpoint is going to generate the height of this rectangle. And then my last subinterval goes from 40 to 60. Here's the left endpoint. The height of the function is going to generate the height of that rectangle, or the value of the function is going to generate the height of that last rectangle. I then came down here and basically just found the area of each of these rectangles I've drawn in the coordinate plane. So I had a height of 2 times a width of 10 for the area of this rectangle. I had a height of 2.3 times a width of 30 for the area of my next rectangle, and then my last rectangle had a height of 2.5 and a width of 20. And if I went ahead and simplified that, I ended up getting 139 meters for the total distance traveled by this person. If one of these velocity values would have been negative, we would have had to change the sign because of the absolute value. So let's say this was a negative 2.3, the velocity of the person at 10. Well, in the velocity graph, that point would have been down here below the t-axis. I would have had to reflect that point up to positive 2.3 because of these absolute values. So the absolute values didn't really affect the way that we could kind of view this little piece of the velocity graph or any of the math that we had to do, but it definitely could have if some of these velocity values had been negative. In part C, we're asked if there must be a time when Ben's velocity is 2 meters per second. And then we want to justify our answer. So the first thing that I always think of whenever I'm asked to determine if there must be one of these, and it can be anything. It doesn't have to necessarily be a velocity that's equal to 2. It can be, any kind of quantity. Must this quantity ever equal a certain value? I initially always go intermediate value theorem. And the intermediate value theorem says if your function's continuous from one value to another value, your graph must cross every y value intermediate to the y values at the endpoints. So what I did was I plotted my endpoint for this interval at 40 on the velocity graph. I plotted my other endpoint on this interval at 60 on the velocity graph. So I had 40, 2.5 plotted. I had 60, 4.6 plotted. If I'm going from this point to this point with a continuous graph, if I just connect them with a line segment, I definitely don't have to cross the velocity value of 2. Now, might the velocity graph dip down here, cross 2, and then come back up and hit the velocity of 4.6? Sure, it might, but the intermediate value theorem is not going to guarantee that there's going to be a velocity that equals 2. It will guarantee there's going to be a velocity that equals 3, since 3 would be intermediate to 2.5 and 4.6. So the intermediate value theorem doesn't really do what we need it to do. Next thing is that I go with the mean value theorem. So the mean value theorem says that a derivative is going to be equal to an average rate of change at least once on a closed interval if you have a function that's both continuous and differentiable on that interval. So I realized that the derivative of position is velocity. So this value, velocity of 2, is actually a derivative or an instantaneous rate of change of position. So what I did was I found the average rate of change of position on the interval from 40 to 60. So I just did a slope calculation using the values from the table, and I ended up with 2 meters per second. So the slope of the line segment connecting 40, 9 and 60, 49 on the position graph is going to be equal to 2. Because of that, I can use the mean value theorem to say that there must be a time when my velocity is going to be equal to 2. The reason why we're able to use the mean value theorem is because a position function has to be continuous. You always have a position. Your position's never undefined. It has to be differentiable because we always have a velocity. The derivative of position is velocity, and we always have a velocity, either moving forward, positive velocity, backward, negative velocity, or not moving, zero velocity. So a position function must be continuous and differentiable. Therefore, by the mean value theorem, our instantaneous rate of change, velocity, the derivative of position, has to equal 2 at least once between 40 and 60, since that was our average rate of change for the function on that interval. And then in part D is a little tricky, but if you start with a diagram, you might realize exactly what you're supposed to do here. They tell you that there's a light above the left end or the west end of the track. And they say that the distance between the person on the unicycle and the light is given by this expression, or this equation. And so I looked at this and I said, well, that looks a lot like the Pythagorean Theorem. And so what I did was I drew myself a diagram. B is going to be the horizontal distance from the person on the unicycle to the west end of the track. The west end of the track is where the light is. So I drew my light post. And then the distance between the person and the light post is going to be the hypotenuse of this right triangle. So L squared, what I have right here, is going to be equal to, well, 12 must have been the height of the light post since I have a 12 squared here, and then plus my B squared across the bottom leg of the triangle. I then said, okay, I'm going to simplify this a little bit, and I'm going to drop the function notation. I'm just going to say L squared equals 144 plus B squared. I want to know what the rate of change of the distance between the light and the person on the unicycle is at the instant in time when t is equal to 40. So I want to know the rate of change of L with respect to t at 40, or the derivative of L with respect to t at t equals 40. So I realized I was going to have to take this equation and do something to it that made a dl dt appear. And what I was going to have to do was take the derivative of both sides with respect to t. So when I do the derivative on the left side here, I end up taking the derivative of L squared, which gives me 2L, But since L is a function of t, I have to finish the chain rule since we have an inner function of t right here, L, and multiply by the derivative of L with respect to t. The derivative of 144 is 0, so that goes away. And then the derivative of this is going to be similar to what we had on the left-hand side, because B is changing over time. This person's position from the west end of the track is changing as they move back and forth along the track. So I did the derivative of B squared, which was 2B, and then since B was a function of t, I had to finish the chain rule and multiply by the derivative of the inner function. Now I was ready to basically plug in some values and solve this for dl dt. So I knew that at 40, B was equal to 9, so I put 9 in place of B. I knew that dB dt, the derivative of position, is just velocity, and at 40 the velocity was 2.5. I knew that at 40 I needed to have a value of L, and I already knew what the value of B was at 40. B was 9, so I went ahead and used my Pythagorean theorem over here to figure out what L was when the light post was 12 feet or 12 meters tall and B was 9 meters, and that ended up giving me 15 for L. So I put 15 in place of L. I divided both sides by 2 times 15, simplified a little bit, and ended up with 3/2 meters per second.